Okay, just to acknowledge my collaborators for a start, honours students like Emily, Ben Walder, who is a postdoc with Malcolm, myself, and also Marky Callahan, who helps in the lab. Look, I'd have to say this is no surprise to any of us, is that we all know that Earth is pretty much an intergalactic plaything and has been for millions of years. We've been bombed by stellar projectiles, which are hit during the Permian and Cretaceous. We've got a wobbly orbit around the Sun. We have plate tectonics generating CO2. So climate change has been with us since organisms have been around. Now, the problem is, has man got any influence in this? And I think the corals tell us the story, is that we know that CO2 has gone up enormously, and Phil showed some nice graphs of that. From 1940, gone from 320 to about 385 ppm. Now, is this due to humans or not? The obvious thing is, if you look at the fractionation of carbon, it quite clearly indicates that man has a role here, in that you can see the depreciation of C13, which is the so-called Zeus effect, that can only be explained by fossil fuels. That is not normal CO2. Okay? It's not CO2 from volcanism, it's not from Hagulbu breathing, it is all to do with fossil fuels. So, given that we have climate change and we have a role, how are we going to monitor this and understand processes that are going to be changed? And certainly on the Great Barrier Reef, that's a huge issue for management. Some of the things that we should expect over the next 100 years are as follows. First of all, average seawater temperature will go up. Present calculations are something like 0.6 to 1.6. pH will go down. We've heard a lot about that. Other things that may change that can have a huge influence on the biota include oceanography, potentially current strength and direction, sea level change, and even through thermal expansion that can be substantial. And Malcolm's alluded to catastrophic ice events, which may cause even greater changes. Another thing of great biological consequence is nutrient input, the kind of the foundation of life, through variation in rain, wind, upwelling and cyclones. Now, cyclones are not just the destruction of habitat. I was out at Myrmidon Reef last weekend, and you can see here massive habitat change on the right-hand side from before and after. What you can also see here, Myrmidon is about here on the most destructive side of Yassi. You can also see that during the period Yassi went past Myrmidon, from these temperature logs we have up there, it actually constituted an upwelling event where the result of the cyclone was sucking cool water up onto the reef. So that's one of the explanations of variation in terms of physical processes on the GBR, is changes in cyclone behaviour. So physical forcing on the GBR, what are some of the main factors in this? Certainly upwelling as I alluded to, along here, which is shown by a chlorophyll signature right along the outer Great Barrier Reef. Inshore we have riverine flow. So these are two major elements to physical forcing. And if you look at this little cartoon here, which is pretty much showing a profile from inshore right to the edge of the Great Barrier Reef, it is environmental forcing that is pretty much driving biological processes. We have upwelling occurring here and riverine runoff occurring there. At the end of the day, this is what matters. It's actually creating food for a whole range of organisms on the Great Barrier Reef, from primary production up to secondary production here in terms of things like copepods. We all know that elements like upwelling are critical drivers all around the world. For example, off California, Peru, the western coast of Africa, even off Albany in Australia, where this explains something like 50% of the commercial harvest and pretty much the rise and fall of societies. You don't have to read Steinbeck's novels to figure that one out. So what do we need to know in terms of the nature of change on places like the GBR? First of all, it would be nice to know about upwelling and runoff as one of the major drivers, and the temporal change of that. Can we actually log how that changes? And importantly, understanding food supply in terms of how that changes through time. Now, it's easy to say that, but it's kind of hard to do. Is that, first of all, if you have ships out there, it's very time-consuming and expensive. Even remote sensing has its limits in terms of how it can measure these things, given that most of these things are subsurface phenomena. And counting plankton, how we all see in lots of labs with jars of plankton, that's hard work to do that at the relevant temporal and spatial scales you need for this type of thing. So, does the answer actually lie with natural loggers? And the examples I'm going to give here focus on Organisms that have annual rings, such as Parietes coral here, showing beautiful bands that are just over a centimetre per year, and also annual bands in the otoliths of fish, where the example I use is primarily Acanthochromous. The other useful thing about fish is that they actually have daily rings in them as well. As if you look at this little guy up here, you can see daily rings from the time of birth up until the time the fish was actually sampled. So there's real potential to look at high levels of temporal variation in terms of what's going on. So for the rest of the talk, I'm going to talk about measuring interannual variation in upwelling and riverine runoff using otoliths, and also using the growth patterns in pre-settlement fishes to say what do these things tell us about the nature of growth in the pelagic environment under different conditions. Now, a great proxy for these types of phenomena is actually barium in terms of measuring changes in some of these signals for the following reasons. First of all, barium does not vary with temperature. So if temperature goes up or down, it's not going to affect the signal. It's a great proxy for upwelling, and here's some data off Myrmidon I've got over here with depth on the y-axis. You can see below the thermocline, I'm running out of grunt here with the laser, below the thermocline you can see that levels of barium are much higher than above the thermocline. As a result of upwelling, this barium-rich water ends up creating a very conspicuous signal to the biota in shallow waters. It's also a good proxy for riverine runoff, and I'll talk more about that. And it complements other elements like strontium, which do vary with temperature, so you can see times of warm and cool in your elemental signatures. Pick your place as well. You might say, well, how do you tell the difference between these different phenomena? If you pick a reef like Myrmidon, it's so far offshore it's not affected by fresh water. If you pick reefs like the Palm Islands, you're so far inshore you're not affected by upwelling. So you can actually discriminate from those two phenomena. If you look at Myrmidon Reef, here's some data from loggers. We had down 30 metres before someone got blown away last weekend, or while Yassi went through. And you can see here there's distinct seasonality in terms of the nature of upwelling. Is those big variations, which are marked as being up to 3 degrees, are upwelling events that represent something like half the annual cycle. And what is very, very clear is that upwelling is occurring somewhere between November and March, and that repeats itself from year to year. I'll draw your attention to the middle peak there, is that upwelling is very strong in that 2006 summer than it was in some of the other summers. Now we can actually see this in the fish. It's a bit unclear. The left-hand side there is actually an X-ray map of an otolith down the bottom here. Right down the bottom you can see it's much lighter. That's where barium is particularly rich, and it corresponds to this blue line up here, which is the core of the otolith where the fish was born. About here the fish matures. Here's its first annual increment, and you can see these little humps here, which I'll focus on in more detail. Now this is about the summertime. You can see here that strontium has dropped off, which corresponds, it's just before here. It's just after the winter where you have a lower peak in strontium. The barium signal is very obvious, is that we know increments are laid down at the end of the winter, and then straight after you can see the barium peak of the upwelling season occurring after that, and it happens every year. So you can actually pick this environmental signal very, very carefully. We've also drilled Parietes offshore at a place like Myrmidon. You can see here variation in the Parietes. The spots down the bottom here correspond to the strength of the signal in the fish otolith. This is that big year of intense upwelling I was telling you about compared to the other 2 years. You can see in the fish and the coral, the intensity of upwelling is reflected nicely in the calcium carbonate structure. If we go near shore, the obvious thing are these big riverine flows that are pumping barium into the surrounding ocean. Now we've measured barium in the water over many, many years, so these are actual data on concentration in the water. We'll run out here. Here's this line here, shows big peaks every summer, which is barium concentration in the water column going up. Around here you can see riverine runoff, so it's over the wet season you get these big spikes. And it is also, yikes, reflected in the otoliths. Now for some reason these arrows have all popped to the side, that they should be a bit further along, but they actually do correspond to about the same places we looked at before, to these annual peaks. So you can see that signal also occurring in the fish. So they're the annuli. What about much finer scales, getting right down to the level of days? Now, this is the sort of temporal scale that's very relevant to the survival of larvae. And what I want to do here is that some of the fundamental paradigms on the survival of larvae focus on the abundance of food. So what we're going to do now is look at the temporal resolution that we have on sort of through the larval life of little guys like Pomacentrus celestis. So what we're going to do when we look at the otoliths is we've demonstrated experimentally that the width of these increments corresponds to the growth of the fish. So there's a positive relationship between width of increment and somatic growth of the fish. We're starting here at the time they're born, and we're going to do a transect right across here, measuring these otoliths to the time that the fish was sampled. And the little guy we're looking at is Pomacentrus celestis, one of the lab rats of fish ecologists, and running from Lizard Island right down to the Capricorn Bunker group in terms of looking at variation. And what you see is that this rather complicated looking graph here, this is corresponding to the primordium, P going out to the edge. So on the left-hand side here's when the fish is born. It goes up to, we've got a little laser thing over, or was this the last chance? This little fish here is halfway through its larval life, and then here's a potential set before they settle and start life as a post-settlement fish. What you can see here is that growth very dramatically increases during that mid-larval phase, drops off a little, and they settle. The important point here is that this is the Capricorn Bunker group on the south of GBR, this up around Lizard, and you can see that growth is much faster when you're on the lower Great Barrier Reef. Okay? Now quite clearly that's potentially a combination of feeding as well as temperature. So what it behoved us to do was to actually do an experiment. And this is with Emily Gerard, is that in this first experiment here, you can see on the x-axis there are 3 levels, low, medium and high. That corresponds to what the fish were fed. The temperatures pretty much correspond to the biogeographic range from the left-hand side there, 26 degrees, through to 31.5 on the right. And the obvious thing is you can discriminate very, very easily between the different rations, like on the left-hand side there, especially the low from the highest. But there's obviously a very clear temperature effect. What was also obvious in experiment 1 is that the differences between 28 degrees and 31 degrees was pretty much all, there was no temperature effect, it was largely based on food. So what it was saying, that sort of temperature range, is that most of the variation in increment width is due to food, not temperature. So you can actually discriminate the difference between the two. In experiment 2, done between 28 degrees and 31.5, you can see that the highest ration is rather even all the way across, and you can discriminate between the different feeding levels. So what we're saying is that if you can carry out these experiments regularly, you can calibrate a relationship to exclude temperature from the relationship, and you know the increments are primarily due to food. And you can actually look at natural variation in the growth of larvae in different places on the Great Barrier Reef. So here we have fishes taken from the outer area of the Great Barrier Reef and mid. And in this particular case, you can see that the fish from the mid, that had their pre-settlement phase in that middle area, fed better than they were on the reef edge. So in conclusion, if you look at these different examples I've given you, aragonite is inert, so it's not biologically active with mitochondria and the like, and it actually forms a natural logger. And then if you look at the annuli of fish otoliths as well as the annuli in corals, is that barium isotopes can provide great spatial resolution through annual patterns to tell us about the changes in upwelling and also riverine runoff, which are 2 of the primary physical forcing influences on the Great Barrier Reef and other parts of the world. Now, with careful choice of sites, you can actually differentiate between upwelling and riverine runoff. If you're like Myrmidon, if you're far enough from shore, you know it's not fresh water. If you're closer in, you know it's due to rivers. And finally, from the otoliths, what we're demonstrating is that rather than sampling plankton every year across the Great Barrier Reef to see how things change, with properly calibrated experiments every year, you can use otoliths as loggers of what's going on out there and use that to actually work out what's changing on the GBR through time. So the big picture is that climate is changing, and with it physical processes that force changes in biological processes. And the biological processes I've focused on is pretty much the production of food. Coral and otoliths of fishes can be the sentinels of change. They can measure what's happening out there and calibrate it through time. I'll leave it there.